Thank you, Brian. Hello, everyone. Good morning. My name is Wojciech Węgrzyński, and I come from Poland. And I would like to talk to you about computational wind engineering. It's a field of science that treats on wind. And in my career, I've stumbled upon some projects where we thought that we should really include wind as a boundary condition in our simulations. We were trying to do it like on our own, how our intuition told us. And luckily for me, I came upon some great wind engineers who showed me the correct way how to do it, not the way I did. And today, I would like to share with you some thoughts, some good practice, relevant information that you might find valuable for you when you have to deal with wind in your simulations. I've separated this presentation into three blocks. First, I will try to introduce you to the computational wind engineering as a field of science. Then I would like to present you why you could actually use this knowledge to benefit in designing natural smoke and heat exhaust ventilation systems. And then I will briefly redirect you to some relevant good practice guidelines that are massively available in this field of science. First, what is the computational wind engineering? And it's a very simple definition. It is a field that relates to the use of computational fluid dynamics for wind engineering applications. And it's actually a very, very big field of science. It can be, you can distinguish four main areas of this field of science. One of them would be structural wind engineering, when you check how the wind affects the structure of buildings. Second would be pedestrian level wind and urban flows, where you test how the wind flow will affect human well-being and people on the level of ground, but also in some parts of the buildings. There's wind-driven rain and snow analysis as well, which focus on how particles move along with the wind, and bluff body aerodynamics, which is how wind does flow around various buildings, various objects. And actually, this field of science is enormous. It has more than 50 years, and to illustrate how big impact it has on all of us who are in this room, I've chosen two pictures. The first on the left is an illustration of Louis Fry Richardson weather forecast factory, and it's a beautiful concept that came in the 20s of last century, so 100 years ago, where Louis Fry Richardson he thought about the concept of using Navier-Stokes equations to estimate pressure fields around the globe, and he figured out a concept where a large amount of scientists would sit around a major room and just pass to each other the results of their calculations. And this is kind of a human-based computational analysis, numerical analysis. It's a beautiful concept, and it took like 50 more years for humanity to catch up with that and be able to do that with computers. So that's a fantastic concept. And on the right, you have the first page of breakthrough article by Węgrzyński, in which he proposed the concept of how to model the turbulent flow, which now we know as LES modeling. So this field of science has impacted us more than you would ever think. And what we fire experts could use this for, well, to make it simple, what we would like to use is just put this, which is wind, into this, which is fire, but in a way that doesn't end like this. And it's not that hard to get into something that ends like this. To make it systematic, to show you where does it come from. Because the computational wind engineering deals with things that from very small turbulent flows to the simulating a whole planet and their movement around the globe. So where are we in this? First of all, we are in the lower part of atmospheric boundary layer, although some of us try to escape that with super skyscrapers with a great success, but most of us are in the meteorological microscale and lower part of atmospheric boundary layer, which defines kinds of submodels we use for defining the wind as a boundary condition, the wind profile thing. And on the scale, we would be pretty much in this area, and things that are smaller than our field, we tend to implement as submodels, which are just resolved along our simulations, and bigger things are usually implemented just as boundary conditions that affect our simulation. And now to go on with how could you benefit from this field of science. And the obvious part is that it's important when you design natural smoke and heat ventilation systems. And why we have taken this approach, it's that in natural smoke and heat ventilation systems, we are still thinking, we're still designing by concepts that are like 30, 40 years old, and they were not really drastically improved among the years. There is a lot of space to be better at the designing these devices, these systems, and I'll show you why. Whatever standard you look, and that's my claim, you will end up with a parameter that will be called the discharge coefficient that will determine the performance of your natural ventilator. And that's like all over the world in European standards, in German standards, in NFPA standards. It always ends up with some form of discharge coefficient that you shall use, put into your equation, and then get the amount of smoke ventilators you shall put on your roof. But this discharge coefficient it's not really the best way how to determine the performance of a natural ventilator. First of all, you might be confused that it's the same thing. Well, there's a lot of discharge coefficients in our field of science, and the reason of that is fantastic work by Prall and Emmons in the 70s, who, using saline water modeling, have proven that flow through doors, through openings, is slowed because of the boundaries, and they determine some kind of coefficients. And this type of approach to use coefficient for flows is very popular in our field. But in case of natural ventilators, this flow coefficient comes from something totally different. It comes from, at least in Europe, from a standardized test. There's a standard called EN 12101 Part 2, which says how you should test your natural ventilators. And what the test does, you have a chamber on the floor, like one I'm standing on, and you push air into this chamber. The chamber is closed with the ventilator you are testing, and this whole chamber is inside a large wind tunnel. And then you push air on this area with a speed of 10 meters per second at a given turbulence intensity ratio. And by comparing the mass flow that enters this chamber and then the pressure difference between inside and outside of the chamber, you determine this coefficient value. So you have to realize that it's just one wind speed that you tested. It's just one range of pressure that you tested for. And thus, it's not a very good representation of fire. Actually, it's not at all a representation of a fire. It's just try to push as much air through an opening as is possible. And it also has an angle sensitivity. This is a picture from the project of the next version of the standard, where after a comparison case between wind tunnels in Europe, it was made that this is actually a calibration study for wind tunnels. If you test these three devices and they fit within the curves, it means that your tunnel is eligible to test wind ventilators, natural ventilators. So this thing changes if you rotate the device. It changes with the size of the device. It changes with opening angle. So there's a lot of small features that will heavily influence the coefficient value. And why it's a problem? I mean, the manufacturers are actually very good at passing this test. I mean, think about Volkswagen. They really figured this out, and they know how to obtain really good values of the CV, which not necessarily translates into a better performance of the device when you put it on a building. And we have done a study on that. And in this study, we've modeled a small building, like let's say the size of this room, with some ventilators on the roof, and we did various wind flow on the building. And as you can see, the ventilators, it's just 3 chosen ventilators out of 12, and each of them acts differently. Each of them had drastically different performance. We had tests when actually some ventilators were sucking air into the room, and some of them were exhausting. And when you test them in that wind tunnel, you have just one artificial condition. So When you do that, you realize that there's much more into natural ventilation than you would thought of by just looking at the coefficients. So this is why we really got into the computational wind engineering and why we introduced that into our analysis. And now let's go to the interesting part. So how to make a not completely terrible wind engineering analysis. And I crossed the good one for purpose, because actually if you manage to make simulation, CFD calculation of a fire in a room with wind, and you could prove by experiment that it's correct, it would be actually a breakthrough. That would be a major achievement in this field of science. You have to know a thing about wind engineering. There's a saying in wind engineers that CFD is wrong until proven. It's a little different than does fire engineers think. As long as it's colorful, it's good. But they really don't trust CFD that much as we do, and they put much more effort into making sure that it's viable. So, of course, we're not able to reach the same level when we try such complex analysis, like using fire and wind at the same time. But we can make it at least not bad. And I've went through a lot of relevant good practice guidelines, and I gathered them together for you in the paper. The references are in the paper, which I would strongly recommend you going at least some of them, and you will find it very beneficial for your own work, even if you don't touch the wind, because it's just, you will have another look on the field of science you're in, which always benefits you, your progress and your development. What are the key elements I would like to discuss? First, the size of the domain, which you saw yesterday as well. Some kind of blockage ratios, boundary conditions, how to model the wind profile, how to make a discrete mesh, how to make discrete time steps, and a little bit on turbulence modeling. Much more is covered in the guidelines, obviously. First, the numerical domain and how you could build the numerical domain with having wind in your mind. I've made like 3 examples. One in which you would build just, let's say this room is our model. In this case, you would model just the room and openings like pressure inlets. So windows would be pressure inlets, and then you can apply like positive pressure gauge on these openings to simulate that positive pressure effect of wind. That would be one approach, and like a lot of years ago, I have done that. There's a second approach which I see often used by some engineers, which is just modeling a small domain around the building, which is like a small, big, medium-sized difference, but it's just not that big domain around them. And then there's the wind approach, the wind engineering approach. And if I had to classify them, the first one's a crime, the second is wrong, and the third is not completely terrible. The problem with wind engineering is, and this is the first thing that hits you, is that with this thing you have to go big. I mean, it's enormously big models, and you have to go over with your mind and comprehend. It's like really big models. You have to go 5 heights of the biggest building you model in your simulation. You have to go 5 widths, and there's good reasons for that. You need the room before, so the wind profile can actually catch up with the roughness of the terrain you model, and actually resolve correctly before it reaches the thing you model, because the wind is just not, it's not just a positive pressure effect. Wind is dynamic. Wind is different on different parts of the building. It's much more complex phenomenon. So you need to give it space to resolve. Then on the sides and above, you need to make sure that the way how you model your domain does not really interfere with your model. And that's also why the blockage ratio that should be used is less than 3%, which means less than 3% of the whole cross-section of the domain shall be your model. And behind the model, these 15 heights is just the space to resolve the wakes that form behind your model, and then they can as well affect you. And to give you a sample how it looks, how does this big domain looks? This is a project we've done in the middle of Warsaw, which was a reconstruction of old shopping mall, and it's actually very close to where I work. And we took a part of the city, and we had to like build it all. So there was no other way to resolve the flows on this facades that had natural ventilators on, then making the whole area being built in a numerical model. And that's actually not enough, because the wind has angles. The angle of attack of wind is very important, and you have seen it before when I shown you the graphs of the CV value with angle. It will change everything. So the domain has to be sufficiently big to allow you the rotation of the model. And because I assume most of you are users of FDS, and I am perfectly aware that this might cause problems if you try to model that in FDS because of the Cartesian mesh, and it's not really that good to just keep rotating your model, because you will end up in some, you might introduce some errors you're not aware of. I guess that there are ways around it. You could just use angled wind, angled velocity profiles on your boundary conditions, or you could go with a method that was shown yesterday, where you just choose the worst case based on like the canyon movements of the area. But it's really important that you model at least some wind angles. And why? Because you need to find a scenario in which you have first the lowest pressure on your inlets and the highest pressure on your outlets. That's the pressure difference between inlets and outlets will determine the performance of your system. And you don't really know before you do that how it will work on your building. And this is why you have to introduce some wind angles. The guidelines go with 12. This is an example of how the results might look, where you have a roof that's filled with natural ventilators, and you can see that there's an overpressure area, there's underpressure area, and by rotating the model, you're analyzing in what kind of scenario, what do you get. I'm perfectly aware that it's insanely computational costs of this analysis, and to save some money, we do it in a simplified manner, because we can cheat with steady-state simulations. And we run just 12 steady-state simulations that give us results like these ones, where you find the pressure fields around your building. And once you're done with that, you choose the worst one, and then just go with transient modeling of fire and wind at the same time. Here are some results of how that influences the results. I'll speed up. To what extent you have to model the details of your devices. Here are some examples of our previous work where we were modeling, but just the devices. It was made for the manufacturers to help them optimize their devices. And like these small elements change the CV value by like 0.02. These motors changed by like between 0.02 to 0.03, and like these elements changed a lot. So that gives you an idea of how big the difference are between models. Next thing is that with such a big domain, you need to stretch the mesh. And wind engineering practices allow for a growth function of like 1.3. It's contradictory with what you would use twice the element in FDS, because, and I believe it's better to follow the FDS guideline, because you should not introduce elements that are not aligned in your model. But eventually, when you grow your model, you should come to an average growth rate of something like that. Another thing is logarithmic wind profile. You have to use wind profile. It's not sufficient to just put a velocity inlet with a constant speed, unless you build enormously huge domain in which the wind profile will create itself by the terrain roughness. And I'll end on, I really hoped I will run out of time before turbulence modeling, and I did, so a mission accomplished. This is, I'll just say about the picture, it's a beautiful picture. It looks like a smoke and a plume, but actually this is a satellite image of Pacific Ocean, and this small thing in here is like an island that's like 50 kilometers long. And that's von Karman vertices that form behind this island, and that's like 1,000 kilometers. And that just proves to you that the scale is just a number. The physics is the same, and no matter what you do, it's the same things that rule the motion of fluid, which we resolve. On turbulence modeling, less is better, runs is cheaper, and there are some hybrid approaches to combine that. And to jump to conclusions, there's a whole field of science filled with great knowledge and information on how to deal with wind in computational analysis. And it's difficult, it's costly, but when you do it right, you can really benefit for that, or you can find a client who will benefit and pay for this tremendous analysis, but it really can be good. And we hope to investigate that more in the future, especially that actually we are building our own wind tunnel. It looks like this at the moment, but so it's a natural wind tunnel at the moment, but it's going to be fully mechanical and hopefully operational in next year. And I hope I will present some more nice drawings that time. Thank you very much.
So we have time for one question. Somebody, okay, first hand up, you win.
Thank you for the presentation. It was really, really nice. And you're uncoupling the wind simulation from the fire simulation. How are you introducing the boundary condition from the wind simulation into the FDS simulation? Are you using a volume, or are you just introducing pressures over the ventilators?
Okay, we cheat and we run ANSYS simulation for wind, and once we find the worst case scenario, we just rerun the same simulation, but including fire and in a transient mode. So it's the same model, but we don't turn the interior of the building until we need it. So first we find what's the worst case scenario, and then we implement that. And in FDS, you would most likely need to I don't know, build a Python script that would just translate the velocities or something from larger model into smaller model, and I guess that could work out. I can imagine it working out. It just would require some work in field of programming. But should be doable to just run some kind of, or you could do as well as we, just build a model without the interior, run some transient simulations for like a minute or something to resolve the flow inside the room, and then have a general good idea what's happening in the room and in the domain, and then just pick, okay, this is the worst case scenario, and work further on it, just building the domain to include the interior fire and just do normal CFD as you would do for a fire with this additional boundary condition being wind. That's what we would do.
Okay, so you introduced in the same model wind simulation and fire simulation.
Yeah.
It makes a huge volume.
Tell me about it. Yes, it does. And that's the reason why you wouldn't like to have 12 fire simulations with the wind. We just did that once for science, and that's enough. And you need to first find the worst wind and then just follow. But we're not computationally ready yet to just do it like this.
Okay, thank you.
Okay, well, thank you very much.
Thank you very much.
It's very good.